player 2 plays 2, then player 1 will get a point. If cards are equal, neither player gets a point. Okay, so none of the points is updated. If let's say for example both player places a card 5. The game continues until all cards have been played. So we have to, you can say here, play. And here if A is 5, it means 5 times the first player put a higher face value card than the second player. That's what it means. If 3, it means score 2. Let's look at the constraints. So test cases input were as highest 10 power 3 and it was n as highest n square. So even if we do, let's say, order of n work per test case, total time complexity will be n into t with this 10 power 5. Even if you, let's say, do order of n square work, so this was order of n work or 3, this 10 power 7. So you can even do order of n square work. So you can go as high as order of n square. Order of n cube won't work. N square log n, yeah, n square log n can work as well because it will be just logarithmic factor. But let's see, like, so this is a good way to bound the time complexity. Now that we have cleared out, let's simplify the question a bit. Let's say we have 2 turns list. Although you may not need this list, but let's say we have 2 turns lists, turns of 1 and turns of 2. So this actually represents in a way that turns 1 of I, it is actually the card played by player 1, right? Player 1, player 1 in the ith move. Similarly for this, but we'll have instead of player 1, player 2. Right, so turns 1 of I will represent the card played by the player 1 in the ith move, and turns 2 will actually be, turns 2 of I will be the card played by player 2 in the ith move. And what is this card that can be played? This card can be played in, you can say 1 to n. 1 to n, of course, exactly once. You'll have to play all the cards, right? So fine, that's one thing. Now then we have defined AB. AB are, you can say, the total scores scored by player 1 and player actually on turns 2 of I, right? And this B is actually summation of 1 for I, for every I in which turns 2 of I is greater than turns 1 of I. In simple words, you just add 1 for all the turns where the first player has, for example, let's say I have A equals to 2, B equals to 3, and total cards in our bags were 5. So 5 moves have to be played because we have 5 cards. A is 2 and B is 3. 3, 1, 2, 3, 4, 5, and this can be 3, 4, 5, and 2, 3. So you can see here that this player is winning. This player is cards, so 5 moves have to be played. And if the turns 1 of I, 2 of I is greater than turns 1 of I, let's try to make some observations. What observations can we make? One observation is very obvious. If total points scored is greater than n, the answer is never possible, right? You can just print no. It is simple, right? So if let's say n is 5, you have only 5 cards to be played, and if A plus B is, let's say, 10, fine. So this is one obvious case that if A plus B, then what about less than equals to n? So is it always possible if A plus B is less than equals to n? We'll have to see. So what happens here? So this means A plus B is actually equal to, we'll have to verify the cases where A plus B is actually equal to 0, A plus B is actually equal to 1, so on. A plus B is equal to n minus 1, A plus B is equal to n. So we'll have to verify these cases, right? So this case we already know if it's greater than n, it's not possible. Now my question is it always possible if it is less than equals to n? Let's see. Now this case, let's see, this is a trivial case, right? So this is always possible. You can have both the scores to be 0, 0. This you can say all ties, right? So this you can say if n was 5, you can just have 1, 2, 3, 4 plus B is equal to 0, right? You can just make sure that both turns of yes we should note. So we have A. Yes, it is indeed possible, and we have to print as well. Possible, fine. So we have an point. What next? Good. Like we can go about it, but if you can observe one more thing, let's see. See, in all these cases, there will be some ties, obviously, right? Because if A plus B is n, of course, there will be no ties. But if A plus B is less than n, A plus B is equal to n minus 1, there will be some ties required, right? If let's say n was 5, and if the total points scored were 4, definitely there was one tie, right? If let's say n was 5 and A plus B was 1, it means there were 4 ties, right? So there will be some ties in all of these cases. So what I'm trying to say here is there will be some ties. Let's say you have 1, 2, 3. Which ties will be there? But let's just fix. Let's say this 3 was a tie and this 5 was a tie. If there was some ties required, we can just fix any of them randomly. In the sense, we can place same value cards there. So there is no way like you turns 1 of I. In the sense, there was some ties required. We can just fix any of them randomly. In the sense, we can place same value cards there. So there is no way like you can just pick any random set of cards, and you can make sure that turns 1 of I is equal to turns 2 of I. Right? For all the i's, where ties is required, right? So whichever ties is required, okay, you will fix some face values and you will make the ties happen there. Okay, so there will be some cards remaining then, and you will have to satisfy the condition A plus B equals to whatever we are trying to achieve. Fine. So what are cards is remaining? Can you see one thing? That a player cannot win all the possible games. I'll tell you why. See, if a player has to win all the possible games here, we will need a card higher than the highest face value, which is not possible because a score can only be, you can say scored, a point can only be scored if you put a higher value face card, right? So if a player has to win all the possible games here, it's definitely not possible because you cannot get a higher face value card than this, right? If you like, you might say then don't make this as you can take 5 here, but if you make 5 here, then you will not have a tie. You will have to pick some cards to be ties. That is for sure. And whatever cards you have left, you will not have a card higher than the highest face value. So what I'm trying to say here is, one again good observation, a player cannot win all the, you can say, moves in case where a plus b is less than equal to n, right? A plus b is less than equal to n. And of course, like this, a equals to 0, b equals to 0 case doesn't count. So you can say excluding a equals to 0, b equals to 0 case, right? Because in that case it's possible. But if a plus b is actually from 1 till n, player cannot win all the possible moves because you will not have a higher face value card than the highest. So this edge case is there, right? So if a is equals to 0 or b is equals to 0, you cannot have a plus b greater than 0 or a plus b not equals to 0, right? So in this case it's a definite no. It's a definite no. Right? Because I already showed you why. You cannot have a higher face value card than the highest possible card available after. The ties. If there were no ties, any which way you don't have the higher than the highest. So yeah, I guess we have come a long way. We have two edge cases figured out when there is definitely no, and we have a case figured out where definitely yes. Now all that remains to check is a plus b belongs to 1 to n, where a is not equals to 0 and b is also not equals to 0. Because we already figured out the case where a and b both are 0. Exactly one of them is 0, right? So in the first case it is yes, in the latter one it is no, and all that remains is to check where both of them are not 0 now. Fine. Now before we do that, let's simplify the constraint a bit. Let's say we are getting some scores a and b for a configuration like, let's say 2, 1, 3, and this was maybe, let's say 1, 3, 2. So here the score, if you wonder, like a is 2 here and b is 1. So a is like, first guy is winning 2 times here, and the second guy is winning this once. Now if you have a configuration like this of turns of 1 and turns of 2, effectively you can achieve the same set of scores like a equals to b equals to 1 if you just have 1, 2, 3 here, and for this 2 you put a 1 here, for this 3 you put a 2 here, and for this 1 you put a 3 here, right? So what I'm saying is, if you have a configuration of scores a, b which is valid, that you can get some moves for it, some reorderings of turns of 1 and turns of 2, you can have a configuration where turns of 1 simply goes from 1 till n. Right, so this is obviously possible. It's very obvious, right? You just sort this, so 1 to n, and whatever their partner was, you can place it. So if you sort this, it will come 1 to 3, and then for 3 there was 2, so I placed it. For 1 there was 3, so I placed it. For 2 there was 1, so I just placed it. This is obviously possible. So if AB is achievable using some configuration of turns of 1, turns of 2, AB is also achievable using some configuration where turns of 1 is simply 1 to n. This is obvious, very simple. Fine. So this is fine. So we have simplified our constraints a bit. That the first player's moves are always 1 to n. That is 1, 2, 3, 4, so 1 till n. Okay. Let's then move on to proving that if a plus b belongs to 1 to n is actually achievable or not. Let's see if n equals to 5 case. Firstly, let's try to see if a plus b can be equal to 5. Then we can think about a plus b equals to 4, 3, 2, so on till 1. Now, can you achieve a plus b equals to 5? Of course, it is also assumed that a is not equals to 0 and b is not equals to 0. Right? So this you already know. Now, what are all the possible values of a and b that you have to check? One case is 1, 4. Then another case is 2, 3. Then another case is 3, 2. Right? Then another case is 4, 1. Right? 4, 1. Now, So there is a clear, you can say, symmetry here as well, right? So if 1 4 is possible, 4 1 is also possible. If 2 3 is possible, 3 2 is also possible. I'll take one more example. Let's say we had n equals to 4. So if a plus b is 4, so it is 3 1. Now what I'm saying is, you don't need to actually check all the possible combinations. If just half of them are possible, rest are also possible. Here, if these are possible, this is always possible. Why? Let's say we had a configuration where first guy was winning 1 time and second guy was winning 4 times. You can just flips the turns list, right? So if let's say turns of 1 here was 1 to n and turns of 2 here was in a way that a was some, let's say 5 and b. What you can do is effectively to get a equals to 4 and b equals to 1, you can just swap these, right? So I guess it's obvious to notice. So there is clear. Let's see if it is possible or not. If we can achieve all possible configuration of a and b. So turns of 1, I guess we have already figured out that turns of 1 will. Let's take a case where a is actually equal to 1 and b is equal to 4. So the first guy is winning only 1 time and the second guy is winning 4 times. Okay, let's see how can we achieve that. So second guy has to win 4 times, right? So what you can do is you can just put this 2 here, put this 3 here, put this 4 here, put this 5 here, right? And put 1 here. So in this case, the second guy is winning 4 times. Okay, what next can you do? Let's say we have a equals to 2, b equals to 3. So what you can again do is you can just pick this 3 guys, right? Pick this 3 and place it at the front. 3 4 second guy is winning in these 3 places, and then you can just place 1 2 here. Fine. What about a equals to 3 and b equals to 2? This is obviously possible because if a equals to and b equals to 3 is possible, so if you have 3 times, so one approach is simply swap turn a equals to 2 and b equals. Make sure that these 1 2 these you have to make sure that the first guy is winning 3 times, right? And second guy is winning only 2 times. Just pick these last 2 guys and place it at the start. So 4 5 will be here, and then of course you know that if you start from 1 2 and 3, this will be smaller, so they will not win. So you can just put 4 5 here and place 1 2 3 here. Right, so effectively, like the strategy is obvious what I'm trying to achieve here. Let's take one more example and then you'll get to know. Like the very simple strategy, you could have also seen it. Let's say then a equals to 4 and b equals to 1. So one approach is obvious. You just swap the turns 1 and 2 for a equals to 1 and b equals to 4. Because if a equals to 1 and b equals to 4 is possible, of course this is possible. You just have to swap the lists in this case. Or there's even a simpler approach. The second guy has to win already once. So you just put 5 here. He has to win only 1 time, so just put that 5 here. And the remaining guys you can put it 1, 2, 3, 4. So yeah, it is indeed possible for a plus b equals to n. The strategy was very straightforward. You could have already seen what is happening. So for a equals to 1, we are starting from 2. For a equals to 2, we are starting with 3. For a equals to 3, we are starting with 4. For a equals to 4, we are starting with 5. And more formally, what we are doing is, if you can see here, the strategy is we start from a plus 1 till what? Till the end we go, right? So, or you can say till the end, or till a plus b, right? So 2, you start from 1 and you go till 5. That is this is what it is, right? So start from a plus 1, you go till a plus b, right? Here, 2 to 5, 3 to 1, 2, 1 to 3. 1, 2. Now what is n minus 1? Okay, let's continue with our same example. Let's say we had 5 cards to play with. So turns of 1 is this only. Now, if a plus b is 1, let's say if a plus b is 4, there will be 1 tie, right? So there will be 1 tie, okay? If it is 3, there will be of course 2 ties required, right? And if it is, let's say 2, there will be of course 3 ties required, right? Because only 2 points are scored all in all. So a plus b is a total point scored, right? And if a plus b is 1, there will be 4 ties required, fine? And yeah, fine. So a plus b equals to 0, we already figured it out. But if you want, we can write it. If a plus b is 0, we have 5 ties. Why not? Okay. Can we just fix some cards where ties will happen? So let's say without loss of generality, what I'm doing is, let's say 1 tie is required. I can just make sure that a tie happens here. That is, you place a 5 here. Okay. So if 1 tie is required, let's say we put a 5 here. And now our problem is, we have cards 1, 2, 3, 4. Right, we have cards 1, 2, 3, 4. And that is n equals to 4. And can you achieve a plus b equals to 4? This problem we've already solved, right? Okay, again. I had to do 1 tie, that is a plus b was equal to 4. So I decided, without loss of generality, let's just fix the cards from the end with ties. So this 5 will go into tie. So now you have 4 cards, right? You have here, whatever it is remaining, there will be 1, 2, 3, 4 only, right? So only 4 cards remaining with 4 face values, 1, 2, 3, 4. And what you have to achieve is total points equals to 4, right? Where n is also 4, that is the cards will be also 4. So this problem is already solved. We just solved it, right? A plus b equals to I'll show you one example, one more example. Let's say the total ties required were 2. Let's say without loss of generality, we are fixing these cards as ties. So if these cards are going into tie zone, what you have is now you have 3 cards. You have 3 cards. That is, you have cards 1, 2, 3. N is 3, and the total points scored is now also again 3. So this I guess you already figured out. This is always possible with a strategy, right? So the question is done and dusted. Actually, is now also again 3. So this I guess you already figured out. This is always possible with a strategy, right? So the question is done and dusted, actually, right? So I guess the question was over here. What is the strategy? Now maybe let's just go through the entire approach once. So I'll summarize everything along the lines. But the question is over here. Now the first things first that we figured out was if a plus b is greater than n, it is not possible. No, we cannot achieve it. Fine. Because total points scored cannot be more than the total number of moves. Okay. What next? Then we figured out if a is equal to 0 or b is equal to 0, then you cannot have A plus B equal to 0. Exactly one of them, A plus B not equal to 0. Exactly one of them cannot win all the games. Right? Exactly one of them cannot have 0.0. So in this case also, it is no. Then we also had one case where if both are 0, it's possible. Right? If A equals to 0 and B equal to 0, yes, this is possible. Fine, and the answer was 1 to n, 1 to n. Another case is where A plus B belongs to, so the last case I'll write here, where A plus B belongs to 1 to n, and A is not equals to 0, and B is not equals to 0, is also possible. The strategy, you already know the strategy here, right? So we start from A plus 1, strategy here, right? So we start from A plus 1. To 0 and B is not equal to 0 is also possible. The strategy, you already know the strategy here, right? So we start from A plus 1, so on till A plus B, right? So we start from A plus B. So we go till A plus B, then okay, you go till A, right? So we go till the bad. So same, let's say there were 6, 7, 8, 9 as well, and all those were ties. So 6, 7, 8, 9, you can keep them as it is. So for the ties, what you can do is you can have A plus B plus 1 so on till n as ties, right? So it doesn't change anything. You just have to arrange A plus B well. The ties you can have it at the end. Fine. So yeah, I mean that's the approach. So this is of course turns of 2, right? So turns of 1 is again same, just 1 to n. Now time complexity here is just order of n, I guess you can already see. So these are just constant time checks. Here order of 2n, and this is also order of 2n. So the time complexity turns out to be simply order of 2n or just order of n per test space, right? And space complexity is order of 1. We are not using any extra space, so we are not actually going to create these areas. We are just going to print them. And one more thing, like you can actually combine this 2 steps, right? So you can include it. So this is actually the case where we have all the ties. So this will print the one in the same thing, right? So 1 to n, and this A plus B plus 1 till n, there is 0 plus 1 till n will print the same thing. So these 2 cases you can actually combine. So that's what you're going to do in the code. So I hope you understood the step-by-step explanation. If you did, please comment understood in the comment section right now, and we can move on to the code, which is actually very simple here. Okay, so the code is pretty straightforward. We take the input, then we check if total points are scored are required to be greater than n. So in this case, it's no, it's not possible. If exactly one player is getting 0 points, it's again not possible because we will not have a value card than the highest card available, and then otherwise it's always yes, print the terms of the first player 1 to n, and then print the terms of the second player, which is from A plus 1 till A plus B, A plus 1 till A plus B, then 1 to A, that is 1 to A, and then A plus B plus 1 till n. So yeah, I mean, that's what the question. Time complexity was n into t, which is 10 square root n cube, which is 25. Space is 1 because we are not using any extra space. Hello everyone, my name is Kathan and today we'll be discussing the problem of max grid construction from the introductory problems of the CSES problem set. Let's begin. Let me read out the question for you. A task here isn't left on the same row and you can set top of the same column, right? So a grid value ij is actually, you can say, this operation, this max is actually called an operation, minimum excluded of all the values to the left of it and all the values to the top of it, right? So you take all the values to the left of a guy, all the values top of the guy, and find out the max of it. That is, find out the minimum excluded number in this set, and that will be the value of grid ij, right? So this max operation is a very common operation in competitive programming. You'll see it a lot of times. So it stands for minimum excluded. Don't worry, I'll take examples. But the idea is, what they're asking is, you'll be given this n, it's a positive integer from 1 to 100, and you have to split a grid, which is n by n, where it is 1. How is this 1 coming? What are the values just before in the same row? 2, 3. What are the values just before in the same column? 0, 2, 3. So 0, 2, 3, and 2, 3. So what is the minimum value that is not present in this set? It is 1, right? Because if you have a sequence 0, 1, 2, 3, right? So don't worry, I'll explain the max operation one more time. But that's the question, and there's one more thing you can look. The constraints are pretty less. So I mean, yeah, let's go to the iPad and try to understand this question a bit. That you will encounter in competitive programming. So I want to spend some time here and build intuition for it. This max stands for minimum excluded, right? So for example, if you have a set, let's say the set is 1, 2, 3. So what does this minimum excluded say is, you spit out the smallest non-negative integer, not part of the set. What is the smallest non-negative integer not part of the set? Non-negative means greater than equals to 0. It is actually 0. Right. For example, let's say you have a set like this, 0, 3, 4. So what is the smallest non-negative integer not part of this set? So the non-negative integers are 0, 1, 2, 3, so on, right? The smallest non-negative integer is 1. So the output here is 1. Spit out the minimum excluded guy, you can say minimum excluded guy in this set. Smallest non-negative integer not part of this set. Now that's about that. Now let's just go through our matrix and try to make some observations here, like what do you see? Now this value here, so I'll just go through a value and try to make you understand what is happening. So this value 5 here, it is actually max of these guys, right? The minimum excluded of 1, 0, 3, 2, and 4. So what is the smallest non-negative integer not part of this set? It is actually 5, right? Because these values are 0, 1, 2, 3, 4. So the smallest not. Let's take one more example then. This 2 turns all the values left of it in the same row. So what is the max of it? So the minimum value which is missing is 2. Grid of ij has to be equal to max of the set. And how do you define that set? That set is defined like this: grid of 0 I minus 1 j, 0 grid of I minus 1 j here, grid of all the guys on the left of it on the same row and all the guys on top of it of the same column, right? So this is just a fancy way of writing it. Fine. So what do you see here? Like, let's try to make some observations and see if we can solve this question. Now one thing straight away grabs your attention is all the diagonal values are 0 in this grid. So II is 0, right? So for convenience sake, I've also written the indices here. Maybe if we can get some idea from the indices as well. So maybe these indices are related to these values, right? So firstly, II is 0, that is all the diagonal values are 0. Then look at this 0th row. It has values like 0, 1, 2, 3, 4. For example, if 0 is at the right, for example, 0 with 0 gives you 0, 0 with 1 gives you 1, 0 with 2 gives you 2, so on and so forth. Similarly, for the first column as well, you can see if you pair up any row value with the 0th column, so what else do you see? Rest all thing is fine, right? So rest all cells are property in the max property that I've written here. Now, if you know a little bit about binary numbers, or you can say the bitwise operations, just by looking at these operations, something should struck in your mind that you know that if you XOR two same numbers, the output is 0, right? So this is a property of XOR. So this plus dot is actually the XOR I've written, or sometimes people write it like this. Like this is the XOR operator in C++, but like this is how you use it in notation, algebraic notation. Fine. So XOR x is 0, fine. And these two should directly tell you, you should remember, relate it, that x XOR 0 is x. So you XOR anything with 0, it returns the same value. And if you XOR two same values, you get 0. Value ij, is it just I XOR j? Right, I'm just making a claim here. Is it the case here? Let's see. Let's try to see some values and then maybe we can prove it. But this is true for first row, first column and the diagonals, because by the property of XOR and by the property of XOR, let's see some more values here. Let's take this value. Don't know the properties of XOR. They are like this. So 1 XOR 0 gives you 1, gives you 0, and 1 XOR 1 gives you 0. So if you have odd number of ones, then the value of XOR will be 1. And if you have yeah, I mean, so that's the thing. If you have odd number of ones, the output will be 1, otherwise it will be 0. Fine. So let's take this 2, 3, right? So what is the binary of 2? So the binary of 2 turns out to be 0, 1, 0. And what is the binary of 3? Binary of 3 is 0, 1, 1. So if you take the XOR here, 0, 0 will give you 0, then 1, 1. The value, the grid 2, 3 is actually 1. Fine, let's take one more value. Let's take actually 3, 1. So take 1 XOR 1. Fine. So you can verify it for yourself by taking more examples. grid of ij, like here in every one of them, will actually be equal to I XOR j. So can you conclude it, right? Because if you can conclude it, the question is done and dusted, right? You can just run a loop for I equals to 0 to n, but we have to prove, right? We have to prove that this is actually the case. Because by looking at this matrix, all the values here are definitely I XOR j, but we have to definitely prove it. So for now, let's just assume we are trying to prove it, right? So what I'm trying to prove here is grid of ij is actually equal to, you can say, the max of all the values before it on the same row and all the values above it on the same column, right? So in other words, I'm trying to prove this value is equal to I XOR j. Now we are going to prove it using a very important method, proof by contradiction. So let's assume that we have a k less than j such that I XOR k is equal to I XOR j. So what I'm trying to say here is you have a cell here ij, right? You have a cell here ij. I'm trying to say that I have a k here on the same row, that is one of the columns here is present such that if I XOR the row number with it, I'm getting I XOR j. In a way, I'm saying that this cell value cannot be I XOR j because I XOR j is already occurring in this row to the left of it, right? So I'm saying I XOR j cannot, like this value cannot be I XOR j, a cell value cannot be I XOR j because this value is already occurring on the left of it on the same row. That's what I'm trying to say, right? So this I XOR k is equal to I XOR j. XOR k is equal to I XOR j. So what I'm trying to say here is you have a cell here less than j such that I XOR k is equal to I XOR j. So what I'm trying to say here is you have a cell here ij, right? You have a cell here ij. I'm trying to say that I have a k here on the same row, that is one of the columns here is present such that if I XOR the row number with it, I'm getting I XOR j. In a way, I'm saying that this cell value cannot be I XOR j because I XOR j is already occurring in this row to the left of it, right? So I'm saying I XOR j cannot, like this value cannot be I XOR j, a cell value cannot be I XOR j because this value is already occurring on the left of it on the same row. That's what I'm trying to say, right? So this I XOR k is equal to I XOR j, right? On the same row on the left of it, I already have this value, so you cannot have this value. So this is my assumption basically, right? So that's how proof by contradiction works. You assume something and then you restore contradiction and you say your assumption was wrong, right? So that's how it is. So here I'm assuming that on the same row to the left of it, I have already I XOR j present. Okay, fine. Now what next then? You have this inequality here, this equality here. Now let's take XOR of I on both the sides. If you take XOR of I on both the sides, what you get is you get I XOR k XOR I, and you get I XOR j XOR I. Now there is a property of XOR. XOR is commutative and associative both. So A XOR B is actually equal to B XOR A, and this I guess here. So this can be rearranged. K equal to 0 becomes k. So this is, you have a contradiction because you already assumed that this k was less than j. You were trying to find this I XOR j on the same row to the left of it, but you didn't find it. So you can say this I XOR j doesn't exist on the same row to the left of this cell, right? On the same ground, so like you can assume a k which is less than I, right? You can assume a k less than I. You can assume a k grid of, right? You cannot have this value before it. So this value is unique, right? But how do you prove that this is actually minimum exclusive OR, right? So this value is unique definitely, that for example this value will never occur here, will never occur here. This value will never occur here, will never occur here. So it will not occur on the same row to the left of it, and it will not occur on the same column on the top of it. But how do you prove this minimum? And now this minimum thing, it is bit, you can say, a trivial thing. You can just observe that for example for the 0th row, it's obvious. If you have 1 here, now you know that this 1 is unique. There won't be 1 here. There won't be 1 to the left of it, which hinders the max construction, right? For example, if you are not sure that this guy I XOR j is unique, that is if it is occurring here or here, then the max won't be equal to this. But at least now you are sure that this value doesn't occur here and doesn't occur here. So this can be the mix. Now how do you prove whether this is actually the minimum excluded? Now this just comes by the nature of how XORs work. So you can just see here, if you see this value, there is 2, 3 here, there is 2, 3 here. So definitely the max is 0 here, right? For example, if you see this 1 here, you have 0, 2, 0, like 2, 3, 0 here, you have 3, 2 here. So by definition, this becomes 1, right? So the way you fill this matrix, for example, even if you look at the 6, you have 0, 1, 2, 3 here, 4, 5 here. So by definition, this has to become 6. So the minimum part is, but you can say trivial, or the way XORs work, you are getting that part. But the important thing was grid ij is actually unique. And if you get this value to be unique, that if you are sure that a grid value, this cell is unique in a way it doesn't occur here and here, just by looking at it, the way this matrix is formed, we can see that this value will be minimum excluded of this and this, right? So you can extend it. For example, this is 0. Why? Because you have 4, 5, 6, 7. You have 4, 5, 6, 7. So of course the minimum excluded is 0. This is 1. Why? Because you have 2, 3 here. You have 0, 2, 3 here. So definitely 1 is missing. So that's the idea. So I mean, yeah, the question is done and dusted. I hope you've got it right. So if you did get the explanation, like, please comment understood in the comment section of the video right now, and let's go to the code part. All right, so the code is pretty simple, right? You take the input n and you just print I XOR j for given, like, grid I is equal to I XOR j, and fine. The time complexity is simply order of n square because you are iterating the grid once. Space complexity is order of 1.
problem from the CP-31 sheet by TLE eliminators under the 900. In an operation, you choose basically two integers I and j, where these constraints are followed. J, I1 is less than equal to j, less than equal to I, less than equal to n, basically two different integers that we're talking about. And I minus j is k. So because I is greater than j, I minus j should be k. And then you swap p of I and p of j. Now what are they asking is, what is the maximum value of k that you can choose to sort this given permutation? Sort means from beginning to end, it has simply an increasing order. Alright, so we'll generalize the problem and see better. They have actually defined the permutation also to you over here, so you can read it well and understand what's a permutation. 1 to 5 come in this, and they so this array right now is not sorted, right? 1 to such like I choose I and j, their difference is k, and then I swap the numbers kept at p of I, or in this case if I have the array name as a of I and a of j. So for example, in this case, assuming I would have chosen I equals to 2, sorry, not I equals to 2, I equals to 4 and j equals to 2, then I would be swapping the number that is kept at a of this. Here is, since we want our target to look like this, as in we want all the numbers to be sorted, question is, what is the maximum k you could have selected for which you would have been able to finally sort a permutation. So in this, like the example that we took, I'm not arguing that k equals to 2 is the maximum. Maybe some other better k was visible. Let's actually look at some test case and argue better. Let's say we have 3, 4, 1, and 2. Okay, 2. Now I'll try to just show I 4. So you have a sorted permutation. These operations k equals to 2. Why am I arguing not anything better than all the other k is the expected time complexity in this problem. All right. So I know that 1 second basically will allow me 10 power 8 elementary operations. All right. And in this problem, it's very clear that one test allows me 1 second. So if I write the time or the number of operations, sorry, for every test, that is 10 power 8. Now, in a test, there are 10. All right. So I 3 operations. All right. Time or the number of operations, sorry, for every cases that is given by this variable t. For all test cases don't exceed a limit of 2 into 10 order with that particular factor. I can say that I'm trying to compare, so not exactly with 10 power 5, you can say 2 into 10 power 5, right? Because that's the maximum all summation of n that can go for every test, and I can try to get an expected idea out of this with comparison to this 10 power 8 that is for one test file. Alright, so I can say that if I have a 2 into 10 is to 5 order, of course I can create something that looks like O of n. Maybe I can create anything above that, O of n log n, that also works. If I go in n square order, that's a problem for me, right? N square won't work. So n square limits are not allowed. Anything below that is fine. N log n, n so forth, and anything below than that up to constant is all good to go. So now I have an expected time complexity in my head. I'm looking for solutions that are not n square. It's basically O of n, best optimized case, or you create something like an n log n maximum. That's the max you can go. That's like an upper bound you can go. Nothing above that. And this is what is going to help me create further ideas. I would not now think in directions which might help or which might actually tend to create ideas that are n square or above. I want to remain below that, right? So this is expected time complexity. Let us now deep dive into the main key idea in the problem. Now the key idea in this problem is very simple. All right, since we don't want a brute solution, that is what we discussed recently only, we are trying to take our focus on, let's say, a single number. All right, what we'll say is, okay, let's say you're talking about a general number pi. Okay, I have an example. Let's say the permutation looks like 3, 2, 1, 4, and 5. So let's just talk about this guy over here, that is this number 3. Now this number 3 is of course sad. Why is it sad? Because this number 3 is not placed correctly. This number 3 right now is at index 1. Of course it wants to go to index 3. To be specific, if you observe, once you actually sort the permutation and you observe at the indexes below that permutation, don't you think that basically every number is below an index which is equal to that value? One number is below one index, two number is below two index, three number is below three index, four number is below four index, five number is below five index. So right now, can I not argue that this 3 number is a sad guy because this number is at the index 1, but actually it wants to go to an index which is itself. So I am saying that right now whatever number is there, it is kept at, let's say, the P of, let's say, index A. Then the index that is right now, that is A index, it wants to go from there to an index B which is actually equal to this value, that is P of A. Yes, that is correct. Now to understand this more better, can I say now if it is at the index A and it wants to go to a new index B, which is actually that number itself, 3 wants to be under the third index, can I not generalize this and simply say that from index A to going to the index B, basically the difference of A minus B, and if I take like an absolute difference of A minus B, this should be divisible by K. Whatever K that we choose, whatever K that actually satisfies everything, this difference has to be divisible, right? And this should make sense. Now, assuming, right, we have already proved that this index B is actually the number itself, that is P of A, we can even generalize it better and say A minus P of A mod, or mod doesn't matter. So to look neater, P of A minus A mod has to be divisible by K, or mod K has to be equal to 0. This has to be satisfied in order to make sure that now the number that is right now at some index A lands up being at some other at some other index that is actually the index B, which is actually the index it wants to go to, made sure by choosing a K which was actually like a factor of this difference. Hence, you now are capable to do the swaps and actually make a movement and try to shift P of A so and so forth to the index that is it wants to go, the index B, or basically that number itself. Let's take a very simple idea. Okay, let's say I have something that looks like, let's say 7, 1, 2, 5, 4, 3, and 6. Okay, now let's just bother ourselves with this 7 guy. Of course, this number is sad. It's at the index 1. It wants to go to the index 7. What's the difference? The difference between these two indexes are, of course, 6, right? 7 minus 1 is 6. So if you choose a K equals to 6, that's fine because you can directly swap these two locations, right? Or if you, let's say, choose a k equals to 3 value, which remember 3 is a multiple of 6, then also that's going to work, because for 7 you can do 2 swaps now. You can maybe do a swap that is, so this is index 1, 2, 3, 4, 5 and 6. So you can do first a swap that actually takes you between 1 and 4 index, and then 4 and 7 index. That's also fine, great to go. And you know that 7 will land up at the last location. So don't you think that k equals to 6 also works, k equals to 3 also works? Or indirectly, if the difference was 6, that is from where or which index it is at, that is A, where does it want to go? The index B, or basically that value itself, that is P of A. If I find a k that is divisible of this difference, then that k is good to go. Great. So I think this is pretty much clear, right? You can draw some cases of your own and understand this simple fact. It's simple observation. Now that I have quoted this statement and this statement makes sense, we of course know that if this is true and it's general, then any a that I put for this particular equation has to be true, which means automatically p1 minus 1 also wants to be divisible by k, right? So mod k has to be equal to 0, right? p2 minus 2, or I think the mod difference is what I should write over here, right? Mod, let's say, also wants to be divisible by k, and so forth. Pn minus n also wants to be, mod of that also wants to be divisible by k, which means that if everything of these sort of equations have to be true, and remember, what's the question? You have to find the max k. Then let's try to just rephrase this whole idea. We want to find actually the greatest divisor of all these numbers, all right? All these numbers, pn minus 1, mod, p2 minus 2, mod, and so forth. So what's this definition actually? It's basically GCD, all right? It's no brainer right now that what we're trying to look for is GCD. So all I want to do now, or all our idea that would remain now, is run a quick loop, and for every PA minus A mod value, just keep on taking GCD, GCD, GCD with some initial value. So we can take our, let's say, G value, that's the GCD of, let's say, P1 minus 1 mod, right? And then we can keep on taking GCD of this G value. So G can become GCD of G, comma, P of A minus A, and we can start A greater than equal to 2. Again, this is a one-base indexing. So this is going to basically get us the GCD value of all these numbers, the greatest common divisor that is there for all these numbers, and that is what our answer is. All right, so let us actually run this whole idea. Why is this working on some test cases? And that's going to be very neat. Let's look at some very harsh test case. Let's just say I'm going to take, let's say, test case this is 1, 5, 3, 4, 2, 6. Okay, so difference over here is 0, difference over here is 3, difference over here is 0. If you take the GCD of these values, don't you think you get 3? Yes, GCD of 0, 3, 0, 0, 3, 0, you get a GCD that's 3. And don't you think that's the answer? Go back. Yes, that's the answer. So you know this is working, right? And why is this working? Because if you would have simulated this in your head, basically these numbers don't need any hampering because they are already placed at the right locations, right? The numbers that would need hampering are this and this. If you just select these two numbers and swap them with a k equals to 3 value, you know that this becomes 5. This idea on some other case also. Let's just say, let's take this case. So let's general purpose 1, 6, 7, 4, 2, 3, 8, 5. 4, 5, 0. This is 4. This is 4. So let's just take the GCD of all the values again, all these differences. We find 4. And yeah, that works because 4 is the answer. And that would mean that yes, in our simulation, in our head, these places would not have any, these one, what becomes 9. Here, by some observation, this problem is going to this problem. We have this test case T that we take. Now, this is where our main idea starts with. We have this k value, right? That's the thing that we want to print. Now, then this n variable, simple enough. And then we take the array input. Now, this is where our main idea starts with. We have this k value, right? That's the thing that we want to print. So initially that's absolute of a0 minus a1, right? Where we start off with, and then we start with the index is 1. Now we go and say k becomes every time GCD of k comma absolute of ai minus, and then we want a 1 base indexing. So we do I plus 1 because we started with the index 1. Now starting with the index 1 over here meant you have already covered index 0, which means you already did 0 base indexing, but we want to compare with 1 base numbers, that is 1, 2, 3, 4, 5 and so forth. So we need I plus 1. So we take the difference of ai and I plus 1, and that absolute difference is compared with k, get a GCD, k updates itself every time, and at the very end, k gets printed. That is the correct answer. So this definitely runs for all the cases over here, and it's going to get you accepted on the platform also.
Hello everyone, my name is Viraj, and today we'll be looking at the fifth problem from the CP-31 sheet by TLE eliminators under the 900 rated questions. Let's go. So I'll be moving on to my CP-31 sheet over here. I have ticked off my 900 rated parameter, and the fifth problem, make it 0. Alright, so let's read this problem. During Zonghao's equal to two integers and equal to an equal now we have all. Now there is a specific operation that is allowed to us, right? You can picturize this over here. I can perform at most 8 such operations. Now what is the target? The target is I want to make this whole at this or under less, right? So what are we saying over here? We can take only this gives which I took while XORing to be 0. So basically this becomes to be 0, 0 and 0 or for some. Alright, great. Out some ideas, but we need a discussion on that part. We know them, and in this problem, since I'm allowed the time limit per test as run in this is 1 second, that's the LT, which is at most 500. So if I want to be very specific, the number of operations per test case would actually turn out to be something like 10 power 8 upon 500. That's the number of test cases. This is like 2 into 10 power 5 order. So you basically are getting 2 into 10 power 5 elementary operations as a limit on every test case. Now this is very important because if I look at n over here, which is in 100 order, assuming that this is like the only dependent variable I have in this whole problem, and preferably this is what would affect my time complexity, I can very well picture that if I run solutions that looks like n square, this is going to work because n being in 100 order, n square means I'm running something like 10 power 4. 10 power 4 is of course less than 2 into 10 power 5. So that's good to go, right? But if I start going in solutions like n cube, that's actually a problem. So if n cube is not allowed, I don't want to go above this. So let's come backward. You have n square definitely allowed. So of course you will have n also allowed. You will have n log n allowed, right? And all such lower time complexities than n square would start making sense. You can go as low as O of 1. And complexities like this, if they start making sense, this tells me that, okay, brute solutions up till n square is allowed. Above that, I would start facing a bit of problem, preferably problem where I get up solutions in n cube order because I want to remain in this 10 power 5 boundary or 2 into 10 power 5 boundary to be specific. Now this is very important. This is giving me the expected time complexity discussion, and this is telling me, okay, don't make solutions that run in n cube or above order. You will, even if your logic is right, you will start getting TLEs. Remain in this limit. Alright, great. So now that this is discussed, we can actually move on to finally getting the whole problem idea. What do we want to do in this? Now the problem's solution is very, very simple if you're able to visualize a very simple argument over here. Alright, so I'll actually pitch up the argument. The argument is, like, you can have multiple solutions to this, but this is a very simple argument. If n is even, then the answer is actually 2. And those two operations which I'm picturizing would be 1 to n and then same operation 1 to n. And if n is odd, then still you obviously want an answer because it's obviously given in the problem. You always have an answer. So the answer is there, and this time the number of operations are actually 4. Those are 1 to n minus 1, 1 to n minus 1, then n minus 1 to n, and then n minus 1 to n again. This is the answer. Now let's try to visualize this. Why is this answer true? And what is actually happening behind the picture? Alright, if you get this part, this would have been very easy, and this argument would make a lot of sense. So before you actually start visualizing this part, let's just clarify a small mathematical outlook in this XORing that we are trying to do, or bitwise XOR that we do. Bitwise XOR in itself has a lot of properties, and one of the properties goes like this. If you take the XOR of the same number with itself, you basically get 0. And this should make sense, right? Let's say I have A as represented in bits like 1 0 1 0 1 1, something like this, and then if I take 1 0 1 0 1 1 again and I do a bitwise XOR over here, then basically from the XOR table I'll draw the XOR. Quickly 0 0 1 1, and then this is 0 1 0 1, and this, if this is A and this this is B, then A is or B in bit format, you basically get a 0 over here, you get a 1 over here, a 1 over here, and a 0 over here. So if you just follow this table quickly, you will see that I am getting all zeros over here. Which is acutely true, because what is happening is, if you take the XOR with the same number itself, you are taking XOR on the, like for every ith bit, you are considering the same bit itself. So the same bit XORed with itself. Once I'll do an operation from 1 to n, that's the whole array, and then I'll do the same operation again from the whole array. Let's see why is this working. Let's say you have an array A, and the numbers are A1, A2, A3, A4, so on till n. Two, in the next line I print 1. This is after you have done the first operation. Now you find the XOR of the whole array from 1 to n. When you do that, you basically create something like this. Now a very important pattern in this is observable, that since final XOR, when you take XOR, 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 XOR to n times n being even, you finally get an array that looks like 0, 0, 0, 0, 0, 0, 0, 6 times 0. In this case, when n was 6, assuming. Fully turned out to be a even XS. Since the array is odd right now, in like not array odd, the size of the array is odd specifically. If I take the first n minus 1 numbers, can I say this is even? Of course, right? If let's say I have total of 7 numbers, then the first n minus 1 numbers would be 6 numbers. So 6 of course is even. So the first n minus 1 numbers are even. Maybe it will be only back down, and then you will have this last n minus 1 number left. This is very, very clear. This is very, very observable. If you pause the video, just give it 2 seconds, you will understand the idea. Very simple. Just take the even logic and put it up to the first n-1 numbers in the odd sized array now, because the first n-1 numbers effectively mean you have an even sized array again. So just take that even chunk up and apply the same logic we learned in the even logic, even subcase logic. And if I apply this back, I know I'm getting total zeros in that whole area from 1 to n-1 after I've performed 1 and n-1, basically these two operations. But now the problem is, remember, in the argument also, we did not stop over here. We had two more operations. This was n-1 to n, n-1 to n. Why am I performing those is very visible. We wanted the whole array to be 0. We are still not achieving this condition. an, that's the last number, is still not 0. That means it needs to be 0. To do that, to make it 0, I need to do something more. That something more is actually this, which is very, very commonsensical, right? It actually involves one more OR property, which is again very, very simple to understand. If I write my next two operations as n-1 and n, n-1 and n, I'll take this to the new page. This will basically mean the third and the fourth operation. So let's picturize this. I am talking to the third operation. 0 with any number we get n, already it is still an, but this position changed from 0 to n. Now this is very fun, because after you have done the third operation fully, if you go to the fourth operation and you do n to n-1 to n again, you basically find the XOR of an gets applied. This is what we wanted. We have finally achieved a 0 at the last position also without hampering other places. Although during the third operation, our second last place was hampered to an an number, but effectively it went back to 0, making all your array as 0. And this is what we wanted. Of course, this is what we wanted. So cleverly, I was able to get all zeros even in an odd-sized array. Now, let's pause the video. This problem, of course, is not a very straight problem to look and get the idea quickly. This was done by drawing a lot of test cases and visualizing a lot of stuff in XOR bit manipulation techniques. But once you get the whole idea and your mind starts thinking towards visualization, you'll be able to see how easy this was. And this is the whole problem. All right, so I hope you like it. Let's actually move on to the code part and see how we can implement it.